Think about the classic picture of an atom. You imagine a dense central nucleus with an electron orbiting it like a planet circling a sun. But according to the laws of classical electromagnetism, this setup is physically impossible. When a charged particle moves in a circle, it is constantly accelerating, and accelerating charges must continuously radiate energy. By losing energy, the electron can no longer maintain its path. Its orbit should shrink, spiraling inward at a higher and higher speed. In this model, every atom in the universe would crash into its own nucleus in a fraction of a second. Matter would have no way to exist. The stability of the physical world proved that the planetary rules of the universe fail at the atomic scale. In 1913, the Danish physicist Niels Bohr proposed a workaround to save the atomic model from collapse. Bohr published a postulate declaring that electrons revolve in specific, stable orbits without emitting any radiant energy. He provided no mechanism for this. He simply stated it as a requirement for the atom's survival. He then defined these orbits with a quantization condition. He argued that an electron can only exist where its angular momentum is an exact whole number multiple of Planck's constant divided by 2 pi. This created a spatial layout where electrons are allowed on specific circular tracks but are forbidden from existing in the vast empty spaces between them. Bohr's math accurately predicted the behavior of the hydrogen atom, but for 10 years it remained a mathematical hack. No one could explain why the electron was physically blocked from those in-between spaces. A decade later, the French physicist Louis de Broglie looked at Bohr's rules and offered a new perspective. Physicists were already discovering that light waves could act like particles. De Broglie proposed the opposite, that solid matter, like the electron, could behave like a wave. This means we must stop picturing the electron as a tiny planet traveling along a path. Instead, the electron is an oscillating wave of energy. In an atomic orbit, this wave stretches and wraps entirely around the circumference of the circle. Because the electron is a wave trapped on a circular track, it must obey the strict physical geometry of waves, changing the rules of the atom. Imagine an electron wave trying to occupy a random orbit where the circle's circumference doesn't perfectly match the length of the wave. As the wave completes the circle, it misaligns with its own tail. The peaks overlap with the troughs, creating destructive interference. As this wave continues to travel and reflect upon itself, the opposing energies cancel out. The oscillation flattens. When the wave's amplitude drops to 0, the electron effectively ceases to exist in that location. Bohr's forbidden zones are the specific locations where an electron wave geometrically destroys itself. For an electron wave to survive, its peaks and troughs must align perfectly with themselves every time they complete a lap. This stable, perfectly aligned pattern is known as a standing wave. This creates a strict geometric rule. The orbit's total circumference must exactly equal an integer number of whole wavelengths. Fractional waves are physically impossible. A wave that doesn't fit the circle instantly collapses, snapping to the next size, allowing a perfect standing wave. Bohr's allowed orbits are simply the specific circumferences where these integer standing waves can geometrically form. The integer n, representing the number of wavelengths, is the exact same principal quantum number from Bohr's model. We can see this in the math. The circumference, 2 pi r, must equal n times the wavelength, lambda. By substituting de Broglie's formula for wavelength into this circle equation and rearranging the variables, the geometry transforms into Bohr's exact quantization rule. This simple geometric substitution derived Bohr's unexplained 1913 postulate, solving a decade-long mystery. Bohr's quantization rule is the physical byproduct of an electron wave struggling to maintain its shape in a circular orbit.